Hello, my name is Thomas Collier, and this is our 2002 Lab Project 1 by me, Chase, Chris, Jamie, and Jacob.
Hi, my name is Chris Yakis, and I'm here to talk to you about the design requirements, including the research and simplifications of our project. The requirements we had to design our balloon around were that it had to maintain an altitude between 26 and 24 kilometers. It must be up in that altitude for at least one whole day-night cycle, and that the balloon had to be able to carry a payload of 500 kilograms. The main point of research we did in this project was around zero pressure balloons. These are typically made of a very thin sheet of plastic or polyethylene film, which is what we decided to use for this project. They are extremely big, as you can see in the bottom right-hand corner with the NASA Big 60 zero pressure balloon. They have ducts that allow gas to escape and prevent pressure from building inside the balloon. And they drop a ballast-like material to stay at the altitude during the nighttime. We split our simplifications into two different groups, the balloon and the whole system. For the balloon, we assumed that the shape was a perfect sphere, it was a thin-walled pressure vessel, and that it was a simple black body. We also had to assume that the gauge pressure was 10 pascals, and lastly, that the helium was not lost from the balloon and it acted as an ideal gas. For the system, we had to ignore transient effects, which means the balloon would teleport to its altitude. We only needed two different time profiles, that during the day and the night. And to find the temperatures for those time profiles, we used radiation dye.
Thank you, Chris. And as for our design choices, firstly, we went with high density polyethylene for our balloon material. This is because of its extremely high strength due to its marginal difference in yield strength and ultimate strength. It has a density of 917 kilograms per meter cubed. And as for the sake of simplicity, we chose a yield strength of 11.6 megapascals based on an average of the system, as the yield strength does change with temperature, though it is a material property. The thickness of the polyethylene was determined to be 25 microns from our findings, which will be more explained later. We ended up choosing helium as our lifting gas for a few select reasons. Helium is a much more reliable gas with it being inert. There are a lot less variable issues that would possibly come up as opposed to hydrogen. Obviously, the Hindenburg being an extremely tragic example of that. And even though hydrogen would create more gross lift per volume, helium is about 93% effective, which only increases our volume by a slight amount. We also obviously used helium in the scale model experiment, providing us with some basis of knowledge on the gas. We settled on a safety factor of 3.64, which is plenty enough for the given problem. This allowed us to solve for that thickness of 25 microns, given our found radius and other given variables, such as gauge pressure being 10 pascals. We did graph the thickness of the balloon against safety factor to show kind of the relationship of the two and where our values lie, as well as the safety factor against volume, given our found thickness. We did have to expand the graph quite a lot, as we mostly wanted to show the exponential relationship between the two. Thank you.
Hey everyone, I'm Jacob Vermeer, and my focus for my part of the preliminary design review is going to be building out our mathematical model and presenting our initial methods and our results. First, I want to talk briefly about our scale model. One of our major takeaway from the scale model is that there has to be a force balance between the upward buoyant force of the balloon and the downward weight force of the balloon system. So naturally, that follows that we start our mathematical model by analyzing a force balance with this free body diagram. We note that in order to achieve neutral buoyancy, these are going to have to be equal, this upward buoyant force, this downward weight force. So we express that in terms of this. The next thing we're going to do is we're going to break down our weight force into its components, which is the skin, the helium, and the payload. So this is the mass of the material, that's the skin, here's the helium, here's the payload. Next, we're going to break up Archimedes' principle. So Archimedes' principle states that The upward buoyant force acting on an object is going to be the density of the fluid around the object multiplied by the volume of fluid displaced by the object multiplied by the gravitational constant. If we just plug that back into the equation we had on the last slide, it becomes this equation. And in order to simplify this, we're just going to divide out g since it's in every term here. So that gives us this equation. Next, we are going to make a distinction between the volume displaced by the object and the volume of the shell. The volume of the shell is simply going to be the volume of a cylindrical shell. However, making the assumption that our thickness of the shell is so much smaller than our radius that it fundamentally changes the equation. So there's an ultra scientific Wikipedia derivation on this slide, which I imagine will be posted, that you can look at and look at in awe. But essentially, we know from our research that the thickness of this balloon is going to be so small compared to its radius that we can make this assumption. The volume of the skin is equal to this expression. Because we assume it to be a sphere as well, we can just say that the volume of fluid displaced by the balloon is the volume of a sphere with the radius of the balloon. I should mention quickly that this is also the radius of the balloon. This is the thickness of the balloon wall. Plugging these into the equation we had 2 slides ago now, we're going to arrive at this expression. In order to solve for r, which is our ultimate goal, r is an extensive variable, we need to define some of these density terms. So first, the density of air we have over here is going to be given by the 1973 US Standard Atmosphere Model. We decided this was an okay point for our design analysis, since this is just this is going to inform a prototype. It's not going to be the actual thing. If we had an actual balloon that we were sending up and it was our final product, we might even have, some of the prototypes have atmospheric density sensors that would somehow measure the density of the air, and we could fine tune our results. But for now, we're just going to use the model, the 1973 model. This mass of the payload is given to us by the people who hired us. It's 500 kilograms, and then the density of material is given to us by the manufacturer. So we stole this from our materials website, and we kind of went for the high end because we knew it was going to change our radius a little bit. This density of helium is going to be given to us by the ideal gas equation of state. Remember, we are able to make the assumption that the density of helium is going to be given by the ideal gas equation because the pressure is very low, the temperature is relatively high. So we arrive at this expression by rearranging the P equals rho RT. This temperature at 25 kilometers is also given by the US Standard Atmosphere Model. And this P abs term is going to be the gauge pressure inside the balloon plus the atmospheric pressure at 25, which again is given by the US Standard Atmosphere Model. And this term right here is just the specific gas constant for helium. That's what it is, yeah. We can then solve our force balance here for this one variable r. Doing that with our just initial things, our initial parameters, we're getting a balloon radius of 15.74, a balloon volume of 16,334, a mass of helium of 81.82 kilograms, mass of balloon material of 71.46 kilograms, which brings our total mass of the balloon to 653.28 kilograms, acting downward. This is just a quick mass budget. Oh, my blood. This is going to be a quick mass budget. So you can see the payload makes up about 77%. If we compare this to our pre-lab, it's pretty different, but I imagine this is because the fundamental conditions of the lab and 25 kilometers in the air are quite different. Also, this took place in a beautiful Boulder, Colorado, where the air is thin and the density of helium is even thinner. So that's it for me. Thank you very much for listening.
Okay, so thus far, we've only talked about the force balance equation without regarding temperature and radiation. And as we saw from the scale model experiment, radiation is going to have an impact on the buoyancy of our balloon. So what impact is it going to have? Let's break it down. So we're given these black body equations, which help us understand the thermal radiation entering and leaving the balloon system. And what we can do is break that down into the heat in the balloon is equal to the heat coming from the sun plus the heat coming from the earth. So that's pretty self-explanatory. And this over here on the right side, the given equations, those just give us coefficients for the different bodies like the sun and earth. So during the daytime, we're going to be getting radiation both from the sun and earth. And using the equation provided in the top right, it can be determined that the temperature of the balloon during the daytime will be 237 Kelvin, which will cause the altitude of the balloon to increase. Now, the problem is at nighttime, the temperature is now going to decrease because we have no radiation coming from the sun. We just have the moon in the sky. So now the only source of radiation for the balloon is Earth. So we can expect that the temperature is going to cool down. So when we calculate our temperature for nighttime, we're only at 180 Kelvin, which is going to decrease our altitude. Now the problem is it's going to bring our altitude way too low, below the target altitude. So we're going to need to bring up some kind of ballast to get it to float back up. So what we're going to have to do is drop ballast at nighttime to get the balloon to rise back into the target altitude. So the conclusion here is that we need a ballast to drop to maintain our altitude during the nighttime. Now the question is how much ballast do we actually need?
Hello, it's Thomas Collier again, and I'm here to talk about our design analysis. So from Jamie's part, we found that our selected factor of safety was 3.64. And then we're going to want to find the temperature of the balloon during the day using the Stefan-Boltzmann law equations, which are these equations right here. And then we can rewrite these equations to solve for the temperature of the balloon during the day, and it looks like this. We can use the temperature of the balloon during the day to solve for the density of the balloon during the day by rewriting the ideal gas law equation, and it looks like this. And then on to part 2. Since the balloon is in neutral buoyancy, we can use a neutral buoyancy equation, which is right here, which is rewritten to solve for the volume of the balloon during the day. And we know all these values now because we just solved for the density of the balloon during the day. So we can calculate the volume of the balloon during the day. So on to part 3. This is how we calculated the mass of the ballast. This is just a force balance equation with G canceled out because G is applied to every variable here. And so our P target, which was the density of the atmosphere at 24.1 kilometers, because that is the lower bound on what we find acceptable for our desired altitude. And so here's a little illustration showing the balloon dropping the ballast so it can return to its desired height. And so on to part 4, to calculate the volume of the balloon during the night, we just do the same thing as in part 1 and 2. By using the Stefan-Boltzmann law equations to solve for the temperature of the balloon during the night, using that to find the density of the balloon during the night, and then finally solving for the volume of the balloon during the night, which factors in the mass of the ballast because the payload no longer has the ballast. And so here are our findings that we found by using those equations, and so here they are.
Okay, great. So in conclusion, and with any future plans, obviously this was a theoretical analysis of an extremely large model system, many assumptions and simplifications, some of which were listed before, would make a full-scale model of the experiment completely obsolete and impossible. There would be a possibility of creating a scale model to a lower altitude with larger equivalent bounds, but there would still be much more research that we would have to put into how our simplifications affected the model, such as wind loading and transient effects, as well as different time profiles instead of just night and day. And thank you.